All right, gentlemen, we are now taking a look at the second part of Chapter 11, and we're going to continue to look at water. We're going to move away from looking at water sources and how water is supplied as a natural resource and all the inner workings of the water on the earth, and we're going to take a look at water use in particular in more detail. This has some specific application to the labs that you've already started on Monday. Certainly the one where you're looking at how much water is used by a typical FUMA cadet, but also some of the labs in terms of safe drinking water and understanding where water comes from. So we have our preview here, just different topics all the way down through. And the objectives, once again, I would suggest you use the questions that are listed as objectives for the study guide, not only getting ready for the chapter test, but these come in really handy in getting ready for your oral exams as well. Now let's look at water use and management. If we look at how water has been handled and treated around the world throughout human history, we understand that there is an issue or a challenge that exists as people in non-industrialized worlds or underdeveloped or less developed countries use water. They use rivers and streams. And what happens is if a body of water becomes polluted in one area, it affects the people downstream. If a body of water is dammed up, it means there's no water downstream. If it's polluted or if it dries up, there's no water downstream. So people downstream traditionally have been affected by what happens upstream. When there's not enough clean, fresh water, this causes problems in terms of consumption, in terms of cooking, in terms of cleaning, and this is a pressing challenge that exists for people around the world in the underdeveloped or less developed nations. The World Health Organization says that more than 1 billion people lack access to a clean, reliable source of fresh water. And I would point out to you guys, if we connect this to some of the things we talked about in the previous lecture, this is people who do not have the industrial capability to dig or drill wells to get down to the groundwater in their area. And so they lack access to clean, reliable source of fresh water because they have to rely on the surface water. They have to rely on lakes and ponds and rivers and streams. And this is notoriously unreliable, not only in terms of the water going away, but in terms of the water being polluted. So the issue is not necessarily, regardless of how it's presented to us, is not necessarily that they don't have clean, fresh water there. The issue is that they don't have the ability, they don't have the technology, they don't have the tools to dig down and get to the clean, fresh water that is in the groundwater. This chart here just shows some of the things that I'm talking about in terms of around the world. Green represents residential use, blue represents industrial use, and yellow represents agricultural use. So you can see, you can compare, for example, North America to Africa or Asia in terms of where most of the water is being used. And we recognize residential, agricultural, and industrial as the three major uses of water for humans. All right, so across the world, if you take all that information on that graph on the previous slide, across the world we see statistically that most of the fresh water is used for agricultural use. It's used to irrigate crops. But we see that different agricultural tendencies exist in different places, and so the pattern of that water use is different. That has to do with the availability of fresh water, has to do with population, has to do with economic conditions. All these ultimately drive how people think about and how people use the fresh water that they're using. Industry is not small. If you notice on the graph on the previous slide, in each of the areas, the smallest use was residential. Industry accounts for 19% of the water used in the world. That's 1/5. The highest industrial use is in North America and Europe. So again, you have industrialized nations. They're going to have more industrialized work, manufacturing, and therefore they're going to use more water in that role. And then we see that the remaining percent is around 10% used by households. So let's talk about residential water use. This looks disparate. It looks unequal when you look at it around the world, from one part of the world to another. The textbook here gives the example: United States, the average person uses about 300 liters of water a day. In India, the average person uses only 41 liters of water a day. Certainly there's a big difference there, but again, I want to stress to you guys, just because the average American uses 300 liters of water a day doesn't mean they're using some of the Indians' water, and that's why they have less. Okay, it has to do more with accessibility. Okay, the average American has very accessible water because we have the technology to dig or to drill down into the groundwater and get it. We have the infrastructure in place to build reservoirs and to pump the water out of the reservoirs into cities. In places like India, in most African countries, that's not the case. And so that drives this disparity of water use as much as anything else. In the U.S., only about half of residential water use is for activities inside the home. So only half is used for drinking and cooking. The remainder use residentially activities outside, watering the lawns. So even though I'm pointing out to you guys that this disparity has as much to do with accessibility as anything else, it doesn't mean that industrialized people aren't wasteful. I think there is, a bit of waste that comes with being industrialized. Working for the sewage treatment plant when I was in college, working for a water district customer service line, you get a feel. You understand where that waste is. People call to complain about a high water bill, but they have leaky plumbing. They have a running toilet. They use their garden hose to fill their pool in the spring. They wash their cars every day. There is what comes with an overabundance and an overaccessibility is possibly an overuse. This table shows how the water is used in the United States per person. Now, in terms of water treatment, we say that most fresh water needs to be potable. We think of fresh water as drinking water, but it still needs to be potable or potable, which means it's drinkable. It needs to be made drinkable. The word means suitable for drinking. And so we have developed water treatment. And water treatment, as you have seen in one of the labs that you're working on, will take out things like mercury and arsenic and lead. Those things are poisonous to humans in even low concentrations, and yet they can be found occurring naturally. Certainly they can get into water supplies unnaturally, but they can be there too just because of what water flows through and what it dissolves. On the other hand, there's lots of other things in water that need to be dealt with before it can be considered drinkable. So let's look at some of those. There are pathogens. Pathogens, virus, microorganisms. Microorganisms can be bacteria. They can be cysts, amoeboid, and these things can get into the water, can get ingested, and then cause disease. These are found in water that becomes contaminated by sewage or animal feces, and usually what we're talking about is some type of fecal coliform. E. coli is a big one, but there's lots of others. And there are lots of ways that we can treat water to get rid of all these different things so that it can be considered drinkable. And the way we treat it, we can treat it physically through filtration, or we can treat it chemically. And most water treatment facilities are actually going to use a combination of both physical methods and chemical methods. This diagram is in your textbook, and I won't spend a lot of time looking at it here, but it shows the different stages of treatment for the water, from filtration to coagulation to more filtration to chlorination to take out the pathogens, so on and so forth. All of this is happening until that water eventually gets to your faucet. Let's talk about industrial water use. We said that industrial water use accounts for 19% of water used in the world. Water ends up needing to be used to manufacture goods, to dispose of waste for manufacturing procedures, and to generate power. And all those are important, especially in an industrialized world. So this pie chart shows that 19%, just about 1/5 of all the water used, goes to industrial use. In fact, the water used in an industrial setting can do lots of different things, but most used in the industrial setting is used to cool power plants. And the way this works is you have power plant cooling systems. They're generating electricity, nuclear power plants or coal burning or whatever, and they need to have the ability to cool off as the equipment gets really hot. The system is driven by heat, and what they'll do is they'll pump water from surface water. They'll build the power plant on a river or on a lake, and they'll carry the water through pipes into the cooling tower. And then as the water absorbs all the heat energy, that water is then released back into the source, back into the lake, back into the river. But it's being released back in very, very hot. Okay, and this has an outcome, this has an impact on the ecosystem of that particular body of water. But the other thing to keep in mind is that water's clean. It's been in a closed system. It's considered clean. It hasn't had any contaminants. It's not taking contaminants out. It's working just like the radiator in your car works. They're enclosed pipes absorbing the heat and then bringing that hot water back out to cool off. Now, in terms of agricultural water use, we said 67% of the water used in the world. We know that plants require water to grow. Plants actually require a lot of water. And as much as 80% of the water used in agriculture evaporates. So this gets to our conversation about how we're using it, our patterns and our habits. And I think it is interesting to note that in what would be considered today some traditional irrigation techniques, 80%, especially in industrialized nations, 80% of that water evaporates, which means it doesn't even actually get to the plants and do any good for the plants. And we have a pie chart here that shows this usage. Irrigation is what we're talking about. It's defined as the method of providing plants with water from sources other than direct precipitation. So when it rains, your crops get water, but they're not being irrigated. Any other water outside of precipitation that is brought to the plants is called irrigation. There's many different irrigation techniques. You can use shallow water-filled ditches, which is a pretty traditional, classic, kind of old-school, non-industrialized method. The U.S. agriculture is an industrialized endeavor, and so we use high-pressure overhead sprinklers, which is the most common form. But we also know that this method is inefficient because almost half the water evaporates, never reaches the plants. And we use it because it works for us, and we have the water. We can just keep pumping the water to get the irrigation levels where we need them to be. But it's inefficient because there are other ways to do it that maybe are a little bit more labor intensive, but actually allow more of the water to be used by the plants. We also, especially in industrialized nations, need to think about development. And in terms of water, this brings up what we call water management projects. Um, People like to live in areas where there's a natural distribution of surface water that's inadequate. And so, what do we do to change that? We build dams, we reroute rivers. We can do all kinds of things in terms of engineering to meet the needs of people who want to live in an area in our modern age where water isn't available. Um, and these water, we call these water management projects, and they have lots of goals. Um, we we can do it just specifically to bring water to a dry area so that people can live there. We can do it specifically to create a reservoir that can hold drinking water. We can do it to create electric power. We can even do it, for more recreational purposes. Although recreational purposes tends to be at least a secondary endeavor, certainly it's connected. We also have what we call water diversion projects. If you want to supply a dry region with water, we have the capability with our industry and with engineering to actually divert a river, part of the river or the whole river, to actually carry the water great distances even to places that need the water. A great example of this out west is the Colorado River. Begins as a glacial stream in the Rocky Mountains, grows larger as other streams feed into it. The river flows south and it's divided, and it's actually divided to meet the water requirement needs of 7 different states. And in fact, so much of the river is diverted for irrigation and for drinking water that, in fact, all of the river is diverted. And the river actually runs completely dry before it reaches its emptying point, the Gulf of California. In terms of dams and reservoirs, we define a dam as a structure that is built across a river to control a river's flow. You've seen dams. Most people understand what the term is referring to. A reservoir is an artificial body of water that usually forms behind a dam. Water from a reservoir can be used for flood control. It can be used for drinking water, for irrigation, recreation, and industry. And in fact, generally speaking, when a reservoir is created, it ends up being used for all of those things that are listed there. Hydroelectric dams are a specific kind of dam that are built over a river and use the mechanical or the kinetic energy of moving water to generate electricity. They do this by turning a turbine in a generator. And at today, where we sit right now, around 20% or 1/5 of the world's electrical energy is still generated using hydroelectric. So it is still significant. Now, when you put a dam across a river to create a reservoir or to capture the energy of the moving water to create electricity, certainly we need to acknowledge and recognize that this is not without consequences. It has consequences. In particular, it has consequences upstream. It has consequences downstream. Behind the dam, the land becomes flooded. And when the land becomes flooded, people and animals can't live there. Okay? So, you displace above the dam communities. You displace people. You pretty much end entire ecosystems. There's a woodland, pasture land ecosystem that can't exist anymore where a giant lake is. Now, to be fair, you also are creating an ecosystem. That lake becomes its own ecosystem as well. But we can't talk about these things in a vacuum and say they don't have any impacts up or downstream. The other thing that happens is fertile sediment builds up behind the dam. Normally, what would happen is you would have farmland on either side of the river, and as sediment comes down to river, it gets deposited and it actually enriches the soil and all of that enriched sediment is now blocked behind the dam, and farmland below the dam or downstream becomes less productive. Not to mention, they also have less water available now for irrigation. And of course, then you have the issue of dam failure. I mean, these dams are engineering feats, okay? They're amazing, but man has built them. You know, even the best have issues down the road. And if a dam completely gives way, if a dam bursts, people living downstream along the river can be killed. It can have all kinds of huge impacts downstream. Talk about water conservation. I kind of have mixed emotions in terms of the whole water conservation movement. We recognize that water is a resource. We've already defined it that way. And we recognize that there is economic formula that are in place. The less water there is, the more expensive it becomes, supply and demand. At the same time, we do recognize also that water is a renewable resource. It's not on the non-renewable list, and it is constantly being renewed because of the water cycle, which we have talked about. When areas dry up regionally, wells are dug deeper, water needs to be piped greater distances, polluted water needs to be cleaned up. That is all increased expense. But I want us to make sure we understand, like the droughts that we've been hearing about in California for the last several years, that has less to do with water usage than it does with weather patterns. Okay, so we need to be careful, in my opinion, when we start talking about water conservation and we start holding people accountable for things that are out of their control. It doesn't mean, I'm not saying that we aren't generally, as an industrialized nation, wasteful with some of these resources. I think we are. But we cannot pin a regional drought on any group of people because they've used too much water, when it has much more to do with the weather patterns and trends over numerous years. So we have to be careful about all of this. Can we conserve water? We can. Can we do less loads of laundry a week? We can. Can we turn off the water when we brush our teeth? We can. Can we reduce the number of times when we wash our car? We can. All of those things are there, and I think they're valuable and worthy to be talked about, but we cannot see those as an ultimate fix for something that is out of human control to begin with. In agriculture, are there things that we can do different? Water loss happens in the agricultural world because of evaporation, because of seepage, because of runoff. So what can we do? How can we increase the efficiency of irrigation? How can we use our knowledge and technology to create ways to irrigate plants that are more efficient? Those are all conversations that are valid and worth having. Drip irrigation, not a lot of evaporation, deliver small amounts of water directly to plant roots. I've used drip irrigation in my own gardens at home, where you buy these hoses and you run the hoses around in the soil, and then they let water solely seep out at a controlled rate. I had great results from year one when I kind of just went out and watered the lawn, or watered the garden, I should say, every evening, to the second year using drip irrigation. I had better growth results, and my city water bill went down considerably. So those types of things really are worth talking about and looking at. In industry, recycling of cooling water and wastewater. So instead of taking the water and using it and discharging it and then taking it back up, creating a closed system where the water is in that closed system and is just used over and over and over again. So you use just one amount within your closed system. Something that is talked about here in Denver, Colorado, pays small businesses to introduce water conservation measures. Saves money for the city, saves money for the business, and residential and agricultural prices as well. So there are things that we can do to encourage a properly balanced paradigm of water conservation. At home, as I said, this is about individual habits, um, creating and using low flow toilets, low pressure shower heads. When, when, as I told you guys in class, when I was growing up, the rule in the house was when you're taking a shower, you turned off the water to wash. So you got wet, you turned off the water, you washed, you turned the water back on, you rinsed, you turned off the water. And my dad was a stickler for that. And my dad was a stickler for that because he was paying a water bill. Not because not because he was worried about water conservation. He was a stickler for that because he was paying a water bill. When you brushed your teeth, you got your toothbrush wet, and then you turned off the water, and then you brushed your teeth. Again, my dad was a stickler for that because he was paying the water bill. My grandfather, so go back 2 generations now, I remember being a little kid at my grandparents' house. If you went in to use the bathroom in my grandparents' house, and you went, for lack of a better term, you went number 1, you didn't flush the toilet. My grandfather saw no need to flush the toilet after you go number 1. And my grandfather was not interested in water conservation. He was interested in his water bill. So just things, we think about habits, we think about patterns, we think about culture and how that has changed. All these things to keep in mind. You water your lawn at night, so more water gets to the grass and less evaporates. All these things are things that we can be thinking about. And again, this table here in your chapter shows a bit of some of the things I've already talked about. Looking to the future, water conservation, connecting that to populations growing, other sources of fresh water needing to be developed. We look at desalination as an option and transporting fresh water. Desalination is basically, guys, you've got the ocean, it's all around us, it's all over the place, it's tons of water, it's salt water, you can't drink it. Can we take salt out of the salt water and make fresh water out of it? And transporting is, how do we get fresh water from point A to point B? Desalination is process of removing salt from ocean water. It tends to be pretty big right now in the Middle East. They have desalination plants. But the problem is, for most of the rest of the world, it's not cost effective. If you're in the Middle East and you got more money than you know what to do with in Saudi Arabia because of oil, and you don't have any water, well then, in your circumstances, you use some of that money, you build desalination plants, you heat ocean water, and then collect the evaporated fresh water. Great. For the rest of the world, it's really not, it's cost prohibitive to do that kind of stuff. In terms of transporting, water can be transported from one region to another. Ships regularly travel from the mainland to the Greek islands, towing enormous plastic bags full of fresh water. Ships anchor in port, fresh water is pumped onto the islands. So that's one example of where we're doing that. You have people who want to live on the island, that's a need, has to do with people's culture and lifestyle. We've thought about the bags in the United States. We've also looked into frozen ice caps and icebergs. 76% of the Earth's fresh water is trapped in those. And, can we tow icebergs to communities that lack fresh water? And we've talked about that, but it's not done because it's not efficient. An efficient way to tow icebergs and tow them to climates where they're melting as you bring them, it makes for a great conversation. Could we make this work? But it's nothing we've been able to make happen yet.